Welcome to the latest episode of Computer Vision Decoded, where we help you make sense of the quickly evolving world of computer vision. In today's episode, we're going to dive into 4 methods you can use to make 3D models from images. We're going to talk about video and image-based structure from motion. We're going to talk about stereo vision and SLAM. And those are 4 different techniques that you can use today in your computer vision applications. We're also going to show this through the lens of how we're actually implementing it today at every point. So this isn't just theoretical. These are things being used to solve real-world problems. Let's jump into this episode. Jared, I'm really excited to have you on the show today. We're going to talk about 4 ways that you can reconstruct a scene using structure from motion, using images to make a 3D model. And you being an expert, have been doing this since you've done your PhD in this sort of line of research. You would be a perfect person to talk about this. And we're gonna talk about this narrative through what we've done at Every Point, which powers stock power reports. And we have Every Point as an API for developers to build all sorts of unique spatial computing products on top of. And but if we go way back, when I started this company in 2013, we had launched an iPhone app to measure stockpiles. And it was magic, but not to you, not to people in computer vision, but it was definitely magic because people were just walking around a pile, taking a video, and somehow they're getting a volumetric report. And so can you talk about the first way in which we can take a video and make a 3D model out of it?
Yeah, absolutely, absolutely. And you already touched on that sort of key word there, structure from motion. So structure from motion at the highest level is a process by which 3D information is extracted from 2D imagery. And so to start, breaking that apart, that 2D imagery could be images, still photos that were taken, could also be a video that was recorded. So there's some flexibility in the kind of imagery that's captured. And then from that imagery, you are extracting 3D information. So you're recovering, where were these, cameras, or where were these images taken in 3D space? If someone recorded a video, how were they walking through that scene in 3D, as well as what 3D geometry was particular points in that image that's triangulated into 3D points in the scene, or are recovering some sort of triangular mesh, some sort of solid representation. So structure from motion encapsulates a lot of these techniques, taking imagery and generating 3D content. Just off a little, side comment. So back during my PhD, a lot of the work I was doing was with structure from motion, but it was for crowdsourced data collection. So dealing with, imagery from different cameras, from different people, from different points in time. You had no control over the capture patterns, the way that people were walking through that environment. So taking that sort of very generic structure from motion pipeline, and now mention what you said here about this, magical, iPhone experience that we built, many years ago, where someone is, pulling out their iPhone, recording a video in this case, and walking around a stockpile, so a pile of mulch, sand, gravel, dirt, whatever it is, but walking around that pile, capturing that video, we were able to then run structure from motion on that video in order to recover the 3D geometry of that pile, in order to generate a stockpile measurement. And so there were a lot of neat things there, and we can dive into them. But like just thinking about, well, how do you take sort of generic structure from motion pipeline, something that can work on all kinds of imagery, and when you're targeting an iPhone or a video, there's a lot of different ways you can tweak the algorithms or accelerate things or add robustness because I'm dealing with an iPhone, or I'm dealing with a video, or I'm dealing with a stockpile, taking that structure from motion and targeting that use case. But yeah, at the highest level, structure from motion extracts that 3D data.
Okay. Well, I'm going to show, my screen accidentally showed earlier. If you happen to be on the non-audio version here, I'm just going to show you guys, here we go, just kind of a video in which the stockpile reports user would take, and you're seeing they just walk in a circle. It's not perfect. We have some lighting issues here, I would say. It's kind of washed out. But that's it. I mean, that's basically all they did to make a 3D model. Let's just play it over again. So like what's happening there? So how are we getting from that to a 3D model? What you touched on there.
Yeah. So a lot of the techniques behind the scene are leveraging features and key points, and motion tracking. So identifying unique parts of that scene or unique parts of that image and tracking it frame to frame. So for instance, this case of, a pile of dirt, maybe there's, a little speckle of, white in there, or a little speckle of dark, or, there's going to be unique points, unique patterns. And so what the computer vision software is doing is it's identifying, thousands or tens of thousands or hundreds of thousands, it's identifying a ton of unique points in that image, and then following those points from image to image to image. So for instance, if there's some point on the front surface of that pile, as I walk around that pile for that first 10 seconds, maybe I'm going to see that point in my view and have seen it from many different angles. But eventually, as I start to move further around the pile, that point has fallen out of my camera's view and it's no longer visible. But because we were able to track the position of that point, in that 2D imagery across many frames, and then from many different camera angles, we can then solve for, well, what camera angles were those, as well as what's the 3D position of that point. So a process of triangulation. So recovering the position and orientation of the camera, as well as triangulating the 3D depth and 3D position of that point. And so if you do this not just for one point, but as I hinted at, tens of thousands, hundreds of thousands, if you do this just for all of the points that you can identify, then you end up with this really dense set of connections, dense set of feature tracks, dense set of key point tracks that have been been followed from frame to frame, and new ones are continually detected. So as I move around the pile, parts of the pile disappear, new parts are appearing, and all of those can be linked together to generate that 3D reconstruction.
Okay, so yeah, I'm gonna, again, for people, if you're watching this on YouTube, I have a visual up on the screen showing kind of what he described. So I'll try to verbally describe what he's saying. But basically, I have this pile. So I just showed a video prior to that and realized I didn't really describe it very well. But someone just walked a loop around a pile of rock. And now what I'm seeing here is it looks like a pile. That pile has a bunch of 3D dots. And then there's this ring of blue around it. And if I zoom in on this screen, you'll see these little green little triangles. And that's, if I click on one, that's just one of the images from that video extracted. And we're able then to triangulate where each of those images are around that pile in 3D space. And then these blue lines are basically connectivity saying, okay, this camera here along this pile or this image also has matched features with other images around the pile, because I'm going to see that part of that pile for several seconds before it's out of view. So that's what it's done. It's just built that connectivity, right? And saying, it's building, we like to call it like a web of connectivity. Stronger the web, the more connectivity points, the better the less error you'll have accumulated throughout this 3D reconstruction. Yeah. So hopefully that makes sense. And so you get some speed ups because we're using video, because we know some things, right? Like, that I can't take an image and then the next image is on the other side of the scene. It's got to be somewhat near the last image that we're using in this, right? So
exactly correct. So there's that sort of temporal information there. So knowing that this is a video, there's only a certain amount of change that can happen from frame to frame within that video sequence. And so instead of starting this search from scratch, we can leverage that temporal information to know that frame to frame there's a certain amount of displacement, certain amount of change that can happen. So that's a way to accelerate it, but then again, you still run into challenges. Like even you said, like that web of connectivity. It's like, yes, it is strong in that each frame may be connected, or have overlapping connections or features that are in common, these key point detections, from 5 seconds ahead and 5 seconds behind. But it is still just, like a single loop around the pile, contrasted with something like, if you had 10 people out measuring the pile at the same time, or like, I think back to my PhD work where I was reconstructing famous landmarks, and there you've got 100,000 photos, of the Colosseum in Rome, or the Pantheon, or whatever it is, other famous landmarks around the world. And so there you have a bunch of different camera positions, ones that are near, ones that are far, both left and right and up, and different elevations. So this, massive, much stronger set, of connectivity, that web of connectivity. Coming here to that video, yes, I have some temporal connectivity, but it is just still a single walking path, usually from like a single distance from that pile. And so there also are some limitations, I'll say, not limitations, but challenges where, because there's, less connectivity than something that's, much more, a generic structure motion approach, we had to be careful when we were designing the algorithms to process that, video-based reconstruction to say, well, hey, let's pay careful attention to those connections, and make sure we're leveraging as much of those temporal constraints as possible.
Okay. So I want to use this technique to not model a stockpile, but let's say I just want to model a movie set.
Yeah.
I would ideally, and so the great thing about videos is it's fast. So if I want to go take images of a set, I know there might be people moving around or things might get moved, and I only have a few minutes. To me, this seems like a great way to go. I can quickly capture lots of images through a video sequence. But you suggest not just, I'm going to go walk back and forth across the set. I should probably walk across the set, move the camera higher, change the angle a little bit. If you go back to our older episodes of Computer Vision Decoded, we do talk about, getting ideal imagery, and that's what we're talking about. It's like you want to not just get like one elevation, one kind of locked direction. We want to get multiple angles as much as you have time to realistically capture. So I should just aim for more. I'm sure there's a point where, I'm not going to take 10 minutes of video of a small little section of a site, but giving 2-3 different viewpoints or elevation changes, things like that will really help strengthen this and get you a better result.
Yeah, absolutely. And to put a little broader context, so here at every point, we've got a, very generic structure for motion pipeline, general purpose pipeline that can process, any sort of imagery we want to throw at it. But what we've done as we've been powering the stockpile reports application, come back to that just for a second, we said, well, hey, because we know we are targeting a stockpile measurement, we can adjust the algorithms, adjust the processing pipeline, adjust the settings to target, that sort of use case so that we know that we're delivering, an accurate, precise reconstruction, of that stockpile from a single loop. If you're now looking at the more generic case of, I'm gonna walk around a movie set, or walk around my house, or other objects, and capture them, then that's when I'm saying, well, hey, I won't necessarily use that stockpile optimized pipeline. Instead would fall back on a generic pipeline, but still having that video is really nice in those temporal constraints. And so as you mentioned, going back to one of our previous podcasts, talking about what are the ideal capture patterns, and combining those ideal capture patterns with that sort of video-based collection technique is a nice way to make sure that you maintain connectivity between your imagery and are able to leverage those temporal constraints in that reconstruction.
That makes sense. All right. Well, let's move along. So we started. Every point started with this stockpile reports, and 2012, 2013, we officially launched a product. Takes videos. We knew that drones were coming on the horizon. And then 2015, I believe, 2016, we started implementing that in the every point pipeline to allow our customers to use drones. Actually, we were actually using airplanes as well. So before that, we were using aerial-based images. Instead of taking a video, you took images. And so instead of a video-based, we're going to image-based structure for motion. So we obviously, there can be some temporal components about it, right? I can say I'm going to take each picture in sequence, but depends on how you go around a scene, that might make sense. So can you tell me, what's the difference there? What is different about using just images versus video? And maybe we'll touch on some pros and cons here.
Yeah, yeah. So just the high level there between image and video is video by default gives you those temporal constraints. If your video is recorded at 30 frames per second or 60 frames per second, you know that there's a really short amount of time between those frames, which means then there's high overlap in that image content. If it was just generic images, sometimes you may not know how much overlap there is. If these are just some random person capturing imagery, there's no constraints about what the overlap is. Fortunately, like you mentioned here with drones, all the most modern drones that you would use for some sort of aerial photography support mission planning. And so you can customize and say, hey, I want my drone to go and fly some sort of grid pattern over a location, and between consecutive images, I would like there to be 75% overlap in that, or 50% overlap, or some amount of overlap. And so there you have some notion of temporal constraints. These images have timestamps, or I know in what sequence they were captured in. So there's a high probability, that two consecutive images are going to have similar content. A difference between a drone flight and a video is, in that drone flight, if that drone, for instance, is flying back and forth in some grid pattern, it may see the same point in the scene, same point on the ground, at multiple different points in time. So if I imagine a grid pattern where it's kind of like a lawnmower, you go up and back and forth. On that first pass, that first flight line, it may have seen something on the ground, and the drone turns around, comes back again, flies another flight line. Well, it may have seen that same point on the ground again, and even like that third flight line as it passes by. You may see that point both within a flight line as well as across different flight lines. Contrast that with an iPhone pipeline, or sort of a video pipeline, where I'm doing just a single loop. It's like, well, hey, there is only one sort of consecutive set of frames that saw that point. And so there's that web of connectivity has a different pattern, a different style to it. Instead of a single path around the scene, now you have this, this grid, this lattice of connectivity between the images, which has its own set of pros and cons.
Yeah. I'm going to share again for our video viewers here. Here's a drone set, and I decided not to show stockpiles. This actually came from Jeffrey Wolf from Jeffrey Wolf Photography, and he sent me this that we processed through every point pipeline, and it was drones. And so if I click on these and show that pattern that we were talking about, lawnmower pattern, you can take off the point cloud, and you see this perfect grid. And that's the great thing about letting a computer handle the images. He just said take overlap of a certain percentage. Each image has actually got they're not exactly straight down. There's some obliqueness to them, but then there's actually a ring around the edge, a whole ring, because we were trying to get around this dome. So you get a bunch of different angles, but you didn't have to rely at least on the drone pilot to get exactly the right image spacing. But if I click on some of these, you can kind of see how they just kind of overlap as you go through. I can click through, and each one is just kind of like the next image in a line, and they're really tightly spaced. I don't know if these are actually progressing or not, but that's what you end up with, is this tight pattern, which is really nice if you have a drone. But if you're walking around with the DSLR, you're doing this human automation, being a human, you're not going to get that, right? So that is a kind of like a great strategy if you can automate, especially capture. Yeah. Or else you really need to know what you're doing. I can also show that connectivity grid for anyone that is watching. So if I turn on connectivity, you see, because we use the computer to decide when to take the pictures, it maintained a really strong connectivity. There's actually less connectivity in the middle here. If I turn on the point cloud, it's just because the dome was much closer to the camera, and so you just don't see as much. The further away objects are, the more you're going to see. So that's what happened there. But still, the computer was able to maintain a really strong connectivity in the structure for motion.
Yeah, yeah, yeah. And so if you think about that connectivity, kind of just coming back to that, one of the key phrases or keywords that comes up a lot in our work, or just in computer vision, is this concept of loop closure. Now, loop closure doesn't mean I haven't, yes, it does apply to the case where I have physically walked around a loop, walked around an object, a car or a stockpile or something else. I've walked around and I've come back to the beginning again. I have completed that loop. I have closed the loop. But more generally, a loop closure is just the notion of revisiting a place that you've already been. And so in this case with this drone, there is a ton of loop closures. Every time that drone, is flying north to south in a flight line, between different flight lines, or in this case, the drone was even flying north to south and then east to west, as well as then a circular orbit at the end. Each of these passes that saw the same part of the scene, but from multiple angles at different points in time, are all just additional loop closures, which have to be discovered via structure from motion techniques. You don't necessarily have those temporal constraints, but it's saying, hey, here's two distinct parts of the trajectory, or two distinct parts of that image set, that saw the same part of the scene. And the computer vision methods need to discover that, and then use those as constraints when they're doing the reconstruction.
Okay. So if you're going to take images, not a video, there's a lot of overlap in strategy. Obviously, you can have a loop closure in both. A video, you want to keep coming back to known places. But in pictures, I feel like it's even more important because we can't rely on the fact that every picture will have a perfect overlap.
Yep.
So that just helps. And so if you're taking this with a DSLR, a mirrorless camera, just taking your iPhone camera, not taking videos, but you're taking, or, any smartphone, just a regular camera, do you just tell people to overshoot? Let's just take more photos than they probably think. And that's what I always notice. Every time I go out and take photos of something, let's say it be a shoe, I'm like, oh man, I think I took like a couple hundred photos, and then I offload them off my camera onto my computer and realize it took like 50. It feels like it was taking more. Yeah. So, it's kind of like take small movements, overshoot. You can always remove photos, but that is the trade-off, right?
Yeah. So yeah. And that's my kind of thing is, you just always be taking photos. So like, a 3D model of a house. Like, 'cause I've walked around my house countless times trying to model the exterior of it for fun, for testing, or for various things. And it's like every time I take a step, take a photo. Every time, every step I'm having a new photo. Because as a human, we look at this house and we're like, oh yeah, it's obviously the same house. I can take 10 steps. It's still the same thing. But that's because we're, our humans, our brains are doing a lot more, than these computer vision techniques are necessarily doing. The computer vision techniques benefit a lot when there's the difference between images is relatively small. It's able to find then connections between those images that don't have a lot of difference, and then link those all together to reconstruct that walking path. And so, a lot of times you want to take even, overshoot, as you said there, overshoot, capture more imagery than you'd expect. Just to help ensure that you had good overlap and connectivity between those still frames. Okay.
So perhaps a question I should have asked a long time ago. Can you overshoot? Can I have too small of a change? Like, let's say I did a 99% overlap. Like, it's practically the same image. Would just any of these structure from motion pipelines use, would they just omit images if it doesn't help? Is that going to... So basically, is that going to harm the result, or is it just not going to really help?
Oh, absolutely. That's a good point. And there's not necessarily a harm to overshooting as long as you're patient. So if you capture a ton of images that have 99% overlap and try to throw them in a reconstruction method, the reconstruction method will give you a good beautiful model. It just might take 10 times longer, 100 times longer, because there's so much redundancy, so much overlap between that imagery. The computation time is just going to go through the roof. It's actually one of the benefits. Going back to the video-based pipeline that we've built at every point, a video has 30 frames per second, 60 frames per second. The overlap between consecutive frames is insanely high. And so if you naively just take every single video frame and try to do a reconstruction from that, those reconstructions are going to take forever. And so we've spent a lot of time optimizing our video-based pipeline to do the optimal frame selections from that. So instead of processing every frame, picking out, well, what is the best subset of frames that gives you a really high accurate result. A lot of times people will say, as a quick shortcut, just take every, 30th frame. So like extract frames every, 1 per second or 2 times per second from the video. And that's a quick shortcut. but that is, there's plenty of ways that can fail. If someone was moving quickly, even in that, 2 frame a second extraction, you may have missed the improper amount of overlap. And so there are trade-offs. You don't want to have too many frames. And so there is a benefit to being a little selective. But again, if I'm going out and capturing these photos manually, it would be really painful to take photos with 99% overlap. You'd be walking around taking photos for forever.
Yeah, and I noticed so talking about the naive way, I call it the basic way of just taking a program like FFmpeg, which can extract images from a video, and if you say, I want 1 frame per second or every 30th frame, whatever it is, there's also a chance that on that 30th frame you happen to have stumbled or shook the camera a little hard, and now it's just saying, okay, now you have a blurry frame. But perhaps 2 or 3 frames prior or after that, you had a really clear frame. So, there's that huge trade-off of, well, now I don't have a good image as a source just because I just took a shortcut, which is a way to go. But again, it's like every point we've done a lot of work just intelligently deciding what images to use. Let's not just pick every 30 frames or every 30th frame. Let's pick the best frame to make this work as you go along in videos. Okay, so
you're exactly right. I mean, that's just to be honest, in my personal projects, if I go out and I'm capturing a video of my house or my car or some environment, I may just use FFmpeg and extract every 30th frame because it's there. It's okay. I did the collect. I was walking at a consistent pace and speed, and I knew that I didn't trip, and and so just as a shortcut, maybe I'm just gonna run this on my machine. I'll run FFmpeg, quick throw through, structure for motion, done. Hey, and I get a great result. But it's when you move from these just sort of one-off tests into a system that needs to support real customers, real users, at scale, users who are not photogrammetry experts. That's when you need to build in this robustness to say, well, hey, what is that optimal frame selection? What is the optimal way to leverage the various temporal constraints, or detect and leverage the loop closures to generate that reconstruction?
All right. Okay. So that makes sense. And that's always think if you're going to put this out in production in the field, you got to make it robust.
Yeah.
You can't make it work just in a lab. Okay. So I want to make sure we have time to keep moving along. So now we've, the one thing I guess I just to put a bow on top of the images versus video, if you are capturing objects and you want them to look perfect for a game, for VFX, images with the high-end camera are going to get you textures. And that is one thing that you will not get optimized with video because you got some motion blur. But again, I'm assuming if you're taking high-end photogrammetry for objects and you're listening to this, you probably are not learning too much. But just know that if you're going to dive into this and want to say, I want to really learn to make objects for game development, things like that, animations, learn to use images. That's the big pro to that is you can get nice textures, better textures. So now we're going to move on. So as the timeline of every point kept evolving, and drones are great, iPhones are great. Perhaps the biggest roadblock to both of those being helpful for solving problems can be that there's a human involved. Specifically for having to operate a camera, walk around, they have to have some knowledge. You can't just have, let's say you put it at a manufacturing site. You can't just say, hey, hey, someone over there, can you go grab some images? They might not know what they're doing. So if you use, let's say, cameras that are always there installed, we call them installed cameras, then you always have cameras where they're supposed to be taking images, and now you don't have a human, and you can take way more images, way more often, solve a whole nother set of problems, and you take that element of having to deploy an actual person out to grab images. And so we started using installed cameras to 3D model environments to give us answers on things like, do I have enough rock for my batch plant to keep producing product for the next 2 days? Things like that. And so in the past, you're talking about a lot of images. We're taking hundreds of photos, thousands of images from a video. With installed cameras, we're using 2 cameras. So I will show a pair of cameras and kind of a 3D model as Jared is talking about that. But so the big pro here is I don't have to put a person out there and it's pretty easy to engineer just two static cameras. But what's different? Like how are we able to get away with such little amount of imagery now and still get a useful result?
Yeah, yeah. No, yeah, two images is, the total opposite end of the spectrum from, where we kind of started with structure from motion. So typically structure from motion benefits a lot when you have redundancy. And so that's why with these, a drone collect, may have hundreds of photos. That video collect had thousands and thousands of frames, in it originally that then we're able to, select the optimal subset from. And so you have this, high amount of overlap, high amount of redundancy. Each point in the scene is seen by, tens of different images from different perspectives, and you get this really high accurate triangulation. So going now to the opposite and saying, hey, I only have two photos, there's a lot of things going on there to make that happen. At the very core is that, well, two images is sort of the minimal amount you need to estimate your depth in the scene. And so if I have two images, think about like your pair of eyes. I have two eyes. My eyes can see a point in the scene from two different perspectives, and so that I can triangulate then a point on the scene because I've seen it from two different positions in space.
So here's the two images.
Here we go. Yeah. So Jonathan's shown an example here. We're at an outdoor site. We've got these materials stacked up between these concrete blocks, and so we've got two cameras that each take a photo from slightly different angles. And not just angles as in the term of like, oh, I just rotated the camera in place. No, it's two physical positions. So one camera's mounted in one position, this other camera's mounted, 10, 20, 30 feet away, depending on the size of the scene. But yeah, so you have this sort of minimal amount of information to be able to triangulate points in the scene. And so you need to pay really careful attention because you don't have that redundancy. I don't have 3, 4, 5, 6, 10, 20, 30, 100 different cameras seeing these points. I just have two. And so you have to pay really, really careful attention to the way you've calibrated the lenses or compensate for distortion. Even though we say, hey, these are installed cameras, it's cameras are still going to move or wiggle. Whether if these cameras are on a pole that perhaps can vibrate or might get bumped, even depending on how the camera and lens is constructed. If there's some sort of autofocus mechanism in there, those lens elements, can slightly shift and move, and so you're going to change the field of view or slightly change the distortion. And so there's some different ways, that the images can be affected or, slightly changed through time. And so it's paying really, really careful attention, to the distortion, to that, the pose estimation, the position and orientation estimation of those cameras, and then that depth calculation, saying for each of these points in the scene, I'm only seeing them by two cameras. So let's be really confident, and accurate in the way that we're doing that triangulation, so that we're able to recover the geometry of the scene and provide customers with answers. So in this case, the EveryPoint engine, we built this, sort of installed camera pipeline where we can say, hey, if I've got, a minimal set of cameras installed at some location that are continually watching something in the scene, we can deliver insights based on that, on what's recovered there. And so in the case of stockpile reports, it's delivering answers about the volume of these piles of material as they change throughout the day.
Yeah, and I'm actually trying to bring up a good visual for that, just kind of show you one of the piles. So here, I'm trying to get it to show on my screen here. But basically, we target a specific stockpile and are able to say, okay, I want to know how much is in that pile. But actually, the interesting thing is you can solve different problems now. Now you got this sort of imagery at a higher cadence. So let's bring up my screen one more time. And now I'm moving to not telling you how much is in there right now. I'm moving into, like how much time left do I have on this pile? So this is a 3D model that we generated just from these two images of that darker material. So again, if you're listening, what we have here is a picture of bunkers of stockpiles. So it's to think of like piles of rock pushed into bins where they have walls around all the sides. Well, one nice thing about having two cameras and walls is that we know constraints. We know the piles can't go outside the walls. So there's some end to the back of them, so we don't need to see the back, so we know where the back is. But from there, we can then take those two images, create a 3D model of those piles and then tell a client, you have 30 hours of material left for production here, or you have 5 hours, and do I need to get more trucks in with that? So that's something you could never do with a drone. I mean, you would not be able to give someone an hourly or every 30-minute update on that. There would be no way, it wouldn't make financial sense to have someone flying a drone. And plus, because Jared, you know all these things about these cameras, with the locations, everything. I can imagine the processing time is just infinitely faster.
Yeah.
Not infinite, but you know what I'm saying is you're not having to figure out where the cameras are in your pipeline. You're not having to then do a lot of those steps that can be very time consuming to get a 3D model. But again, a lot of limitations. I can't move those cameras. They have to be where they are. Those cameras do move, so there might be some error. It's a unique way to get a 3D model. It takes, I think, a little bit more know-how of what you're doing, a little bit more setup. But if you want to monitor things, I want to know if a rail car is there and if it's something's out of spec, because I get a 3D model of the rail car every time it's in a specific location. I have camera set up in the right location. I might be able to alert, or someone who manages those rail cars, things like that. Try to think of examples where this is very useful. And I think indoor environments are always easier. You don't have the elements, but you're trying to track things in a warehouse, trying to figure out how the volume of things piled up in a certain area every day. So if you're in spec for something that should or shouldn't be there. So and then you also, with all these, there's machine learning we can use. So, but the great thing about having these static images is I can start to learn things about the scene. I can throw images into and train on data, saying every time I know these are here, we're going to put that as part of our annotated training set. We know we're going to get good photos. So there's a lot of applications you can go from having these installed cameras that are uniquely exciting to me, as opposed to just having to have a human out there with a camera, or even a robot roving around with a camera, being a drone or a rolling robot, something like that.
Yeah.
You just
I can echo that back. I mean, it's the same thing with me. It's like the kinds of answers that you can deliver. Like you said, if someone has to go out with a smartphone or a DSLR, so if someone has to go out with a camera or a drone and do a measurement, well, then you're only getting those measurements when a human took the effort, took the time to go out and capture that imagery. And capturing that imagery, it takes a certain amount of time. It takes a minute or two to walk around that pile. Mm-hmm. It takes tens of minutes perhaps to fly that drone. And so it's not a continual feed of imagery. It's imagery captured at very discrete points in time. Whereas contrasted with this, sort of installed camera application, now I've got this camera that's watching my scene. In this case, a stockpile. Like you said, it could have been a warehouse, a shipping yard, where you can be looking at objects and cargo and vehicles, and understanding, well, how much is there, how is it moving, when did it move, and understanding the dynamics of that scene instead of just sort of the static nature of it. Mm-hmm. So going from these static measurements of environment, static reconstructions of environment, to, again, we can do discrete static reconstructions from these, from an installed camera, but then also adding that to the layer of, well, no, now it's a much higher frequency. Mm-hmm. We can see things moving through that imagery, understand what its depth is in that scene, and use that to deliver answers that are derived both from the 3D geometry as well as just the 2D semantics. As you mentioned, they're touching on the machine learning component.
Mm-hmm. All right, so I'm going to move on to the fourth and final method, in which, at least at every point, we've been using imagery and doing 3D reconstruction. And this one to me is really exciting. I think it's kind of earned its place into everyone's pocket. It's using SLAM, using basically really fast ways to model a scene in 3D. And as we're seeing the iPhone's AR kit suite of tools, come onto the scene with the iPhone. Actually came out before the Pro versions, but even with the Pro ones and the LiDAR, we're seeing all of a sudden people just waving phones around, getting 3D models, and it's magic. It's using imagery. So I'm going to actually tease basically how we are using it to our fullest, I would say, not the LiDAR, but using what's called SLAM, which Jared's going to explain to us what it is in a minute, but we're using it to measure stockpiles now in like seconds. So he's going to talk, and I'm going to pull up another video again showing that stockpile I showed at the very start where someone walks around, takes a video, does a stockpile measurement. In 2012, that took like 18 hours to turn around a result. 2022, 2023, we got that down to, half hour, something like that. But now we're able to do it in like seconds on an iPhone. So, Jared, what's SLAM, and how is that unlocking us to be able to measure on an iPhone in like a minute or less, a stockpile, making a 3D model that we're able to learn a lot about things from that.
Yeah, absolutely. So SLAM, just to break that acronym down, SLAM stands for Simultaneous Localization and Mapping. Okay, what does that mean? That means simultaneous localization means I am understanding where my camera is in 3D space at the same time as I am mapping that space and creating a 3D model of it. So it's very similar to the goals of Structure for Motion, where Structure for Motion is also trying to recover the position of my camera as well as the geometry in the scene. But instead of doing that in sort of an offline post-process mode, SLAM says, hey, I need to be doing all of this 3D estimation in real time as that camera is moving. The most frequent case you might see, why would I need SLAM? Maybe it's because I'm doing an augmented reality application where I'm superimposing virtual objects on top of the real live footage that I'm seeing. This is also used a lot in robotics. As a robot is navigating environment through a warehouse, through a city, autonomous driving, that vehicle, that robot needs to understand where it is in 3D space as it's driving, so that it doesn't, crash into things and do the wrong stuff. So SLAM is 3D reconstruction, but in real time. And you mentioned their AR kit. So that is Apple's sort of take on SLAM in order to power augmented reality applications. So it's not sort of a general purpose SLAM method. It doesn't expose the accurate 3D seam geometry. And the pose estimation that it's doing doesn't have to be perfect. It just needs to be good enough for augmented reality applications. But it is now yet another tool in the toolbox that at every point, we can use when we're building computer vision systems.
Yeah, and so actually, there's two things I want to show. So early on, when we started to really see this kind of happening live on an iPhone, or actually an iPad Pro 2020 model came out, and Jared, being as he is, loves to get his hands on these things and just test like an engineer would and see where it works best, where it doesn't, so we know how to use it. He posted on his Twitter feed, out of all things. So let me share my screen here. So if you follow Jared, he's at Jared Heinly, and I'll make sure he's on the show notes here. But he actually really dove into the sensor, and he's got a great thread of tweets, and I'll make sure I kind of link these into the show notes. But he was walking around and doing like, this is like a city block that he was in real time getting points on. It's usually in the tracking of the iPhone, which is doing SLAM. But what I thought was really cool is if I go, one thing he notices, like he said, it's not perfect. When he came around to the end of the block, we had two storefronts, but are obviously the same storefront, and they're in two different locations. So that is one thing that can be corrected after post collection there. But that is something to know about. It's not perfect. It's doing fast ways to then relocalize you, figure out where the scene is fixed. But that's where like loop closure really helps.
Yep.
And sometimes waiting longer might be better, but sometimes, how often are you walking around a city block? If you're walking around a much smaller scene, things are not going to drift very far apart. If they do, it's going to be, you might not even notice, or it might be really small. So, kind of know where, what you need. I'm seeing a lot of SLAM too. I was at a conference where they had a lot of like Navis and GeoSLAM has all these different LiDAR SLAM sensors, and they all have imagery on them, all these cameras as well. And, they're not as good as these traditional scanners that take a lot longer, but hey, it's fast and there's a little bit more accumulated error, but to people, it's like, this is a great way to get data pretty much in real time that you wouldn't, you would not be able to do any other way.
Yeah, yeah. And just to highlight what's showing here, I mean, this is that's a powerful visualization, seeing that, hey, if you walk around an entire city block, you end up roughly near where you start. So if I come back to that same, storefront, in this case, ARKit's estimate of my camera position was relatively close, but there's a noticeable gap, over that, 500-foot walking path. I end up at the end with a 20 or 30-foot distance between there, which is great for rough visualization. But if you're trying to do any sort of measurement off of this, or have this look like a single consistent model, it's not good enough. And so that's because in ARKit's implementation of SLAM, they're not doing loop closure detection. And so it's this notion of, hey, when I return to a point in the scene again, make sure that lines up with what I had seen prior. ARKit's designed for that augmented reality application where all I care about is just, does my current augmented reality view make sense? It's not that, hey, if I came back to something 30 seconds later, is it exactly where I left it? And so there's some trade-offs there in the way that ARKit is designed and sort of the use case it's going after. Yeah. But this was what it was nice for me as sort of an engineer saying, well, hey, I now have access to a SLAM system that's been optimized by Apple for iOS devices, and I can use that as yet another input, and you leverage our own SLAM, implementation or our own structure for motion algorithms to accelerate and improve the results here. And so as Jonathan mentioned, now with stockpile reports, we have this capability where someone can take their iPhone, walk around a stockpile. Maybe they spend a minute walking around that pile, but within 5 seconds after they complete that loop, now they've got a reconstruction and a volume report, and they can see that 3D model of their pile along with its volume right there on the phone.
So again, if you're listening on a podcast, you don't get to see this visual, but if you look at SR Measure, which is the application that we have launched this on, you'll see all kinds of marketing content we've put out there, some examples in real time. But yeah, look at that. Jared, what are all these dots I'm seeing on the screen? So what you're seeing is a camera replaying, walking around a stockpile rock, and there's dots appearing all over the scene. What is that?
Yeah, so the dots, that's a preview of some of the features, some of the key points that are being tracked through the scene. As I mentioned before about, well, how does all this work? Well, it works by identifying common parts of the scene and following them from frame to frame. And so that's what these colored dots are providing you as a preview of a subset of those points, saying here are the parts of the scene that we found. And then as we see those points from frame to frame to frame, they start changing colors. And we built into the app, as you finish and come back to the start, an arrow appears saying, hey, you're almost there, keep walking. And then we run that computation. You can even see part of the model, kind of the preview being built in real time. And then once we've optimized that model, solved, handled all the loop closure constraints, optimized for accuracy and precision, then we compute the volume and can deliver that volume report right there on the phone.
Which is amazing.
Yeah.
I mean, considering it took 18, 24 hours, I think even longer in 2012 for us. Now on the iPhone 14, the speed of the processor, the tools, the SLAM, everything is amazing. So this is I'd say it's a great foundation. Even if you're just using ARKit without any other modifications, it might be all you need. If we always like to joke about you're putting a dancing dinosaur on a tabletop for some sort of augmented reality application, and you're doing a small space, your desk, a room, the air is probably not a problem. You probably don't need to go to the lengths, but you can even then take ARKit and you can use someone like Jared or Every Point. You can always build on top of that, and we can make much better, end use application of that. In fact, by just adding a little bit more computation on top of what you get from ARKit.
Yeah.
So it's
that adding that extra computation, to me, that's sort of like the secret sauce. Computer vision as a whole is a very powerful tool. But it's a very broad and generic tool, and so it's how do you take this tool, which is computer vision, and apply it to a particular application, a particular business problem? Are you trying to measure the volume of a stockpile? Are you trying to create a beautiful 3D mesh of a house? Are you trying to track the activity of cargo as it's loaded and unloaded from ships at a shipping port? So you have each of these different applications, where I'm using computer vision as a tool to solve a particular problem. And so it's how then do I use that tool in the best way possible for that application? How can I modify that tool? And so that's what we've done here to build EveryPoint, is saying, well, hey, we've got structure for motion, we've got computer vision, we've got SLAM, we've got this computer vision toolbox. And then as you tackle different applications, that toolbox can be tailored. And I'm going to pull out my Phillips head screwdriver instead of my flathead, or I'm going to pull out this kind of wrench instead of this other one, because I know that for this particular problem, it has the accuracy, the precision, or the performance trade-offs that I'm looking for that particular problem. And so that's why I love thinking about this, thinking about how do I take computer vision and apply it to different problems. And so you see it here with SR Measure. It's saying, well, that's a very specific problem. We're measuring a pile of material, and the user's doing a loop around that, and they're capturing video, and we've got sensor data and visual imagery. So how can I pick the right tools from my computer vision toolbox to deliver that answer as fast as possible? And so it's a fun way to I absolutely love building applications like this and thinking about how do you take computer vision and really tailor it to particular applications.
So what's the future from here then? I mean, it's hard to get quicker than that. You basically, the time it takes to walk the pile, I guess that's where we get into automated drones and robots and things just walking around, capturing, and then it being uploaded. So kind of like along the lines of our installed cameras, but now you're starting to get this on. We've explored cable cameras. We've explored all sorts of rolling robots, walking robots, flying robots. Yeah, that's why we're into it, because again, human can be the one roadblock here. We've got it down to seconds, but you still got to have someone there.
Yep. As
that goes away, we can get data really fast. We can solve a lot more problems that way. I guess the other frontier I speculate is as we learn more and more and more about environments that you constantly are mapping and turning into 3D models and imaging, eventually you just become context aware. We'll know off of a few images how big something is, and that's what we're starting to see in like AI, starting to train neural networks and different sorts of algorithms just to recognize you have plenty of material. You don't have enough material. It's time to order it just off of a single image. So not to say that's the solution you need, but yeah, it's hard to see where we go from here, except for taking humans out of it, because we're the roadblock. We're the slow part.
Yeah. You're spot on. You're spot on. In that road to digitization, of supply chains and assets in the real world, humans are the bottleneck.
It's hard to believe, but it's true.
Yeah, that's what it is. And so it's now, and that's coming back to that installed camera case, like you said there, with installed cameras or robots, it's automating that digitization process. Because once you can automate that, now you can get answers and insights in real time. And then drive business applications or drive real answers for real customers and consumers.
Well, Jared, I think this was very informative. Hopefully people who are not even in computer vision, but are just trying to understand it, I think this might really help them to say there's more than one way to get a 3D model. There's pros and cons. I wouldn't say any one of these 4 ways is the best way. It's what's the way that you need for what you're going for. And then, yeah, I think if people want to learn more, then they reach out to us. They reach out to people who are trying to educate everyone. I'll steer you in the right direction. If you ever talk to me, Jared, same as well. If you connect with him online, try and figure out what the best method is for you, and how, it always kind of starts with what's your end goal, right? So you can engineer whatever you want, but it's deciding what's the most elegant solution to get us there. So all right. Well, thank you. This was really helpful. I'm excited to see what else we build here at EveryPoint and we can showcase. But I thought this was a great way just for people to learn through real world examples of how we've used it. And again, Jared, how do we find you online if people want to follow you? I'll make sure you're in the show notes, but go ahead and throw
you can find me on Twitter, at Jared Heinly, or also on LinkedIn. Again, Jared Heinly.
All right. And I'm Jonathan Stevens, or at JohnStevens85 on Twitter. I'll link those in the notes here, and I will see you in the next episode, Jared. Thank you. Well, that's a wrap. I hope you enjoyed this latest episode of Computer Vision Decoded. Don't forget to subscribe to our podcast on all major podcast platforms. If you watch this on YouTube, you can also subscribe to the EveryPoint channel to get all the latest episodes if they come out. I want to give a big thanks to Jared Heinly for joining us on this episode, and I'll make sure we see you in the next one.